Hello, chemist. Jolly here. These are going to be a series of mini lectures on the reactions of alkenes and alkynes. So let me jump over here. All right, we are actually going to follow the reference sheet, but we are going to do the reactions of alkenes and alkynes. So I'm going to follow the lecture notes. And I'm also going to go down the reference sheet. All right, let's go ahead and get started. So I'm pulling up the lecture notes for alkenes and alkynes. All right, so basically we have to talk about what an addition reaction is. And I know we've done that in the past, but let's just do a basic mechanism. All right, an addition is breaking a pi bond. Okay. Oop. One, you're going to break a pi bond. You're going to make a carbocation. And then you're going to do something to that carbocation. All right, so let's just look at one. We're going to take a generic alkene. And remember, in this case, the alkene, the pi bond, is the nucleophile, so I need to give it an electrophile. And so I'm going to do one of our reactions because it's very visual. This one is called hydrohalogenation, but we're just going to use it as a mechanism. All right, the pi bond attacks the hydrogen. The hydrogen can only have one bond, so it has to give its lone pairs up. All right, when I break the pi bond, there are two spots. Different color. There are two spots right here and right here that could become the carbocation. I don't know, it's not writing. There we are. Okay, we need to use Markovnikov's rule. Okay, and remember, Markovnikov's rule says the most substituted carbocation is the most stable. So that makes this one the most substituted carbocation. And so the hydrogen goes here. Okay, so this hydrogen is now right there. And now we have a carbocation. So we have done the first step. We have broken our pi bond and we have made our carbocation. Right here, if you ever go through a carbocation, look out for rearrangements. And in this case, I have made the most stable carbocation. And in each direction, in this one, and this one, there's no reason to do a hydride shift or an alkynide shift. So there's no way to make it more stable. All right, so we have got our carbocation. And now what is going to happen to our carbocation? Well, there's always a nucleophile around, specifically with the one that I did. So I have a chlorine floating around. And so that chlorine is going to come in and it's going to react with the carbocation. Now remember, the carbocations are flat. I'm going to put it down here. Carbocations. One, look out for rearrangements. And two, when they react, they are flat. Okay, they're sp2 hybridized. So you have to attack from both the top and the bottom, which means if you make a stereocenter, you're going to get a racemic mix. All right, so I'm going to draw that, showing that I can attack from the top and the bottom because it's a mix. And in that case, my product looks like this. And the squiggle, okay, means both. Now, if there's a stereocenter, it of course means both enantiomers, but the squiggle just means you get both combinations. This one doesn't happen to be a stereocenter because they're both methyls. All right. Basically, you take a pi bond, you attack a nucleophile, you create a carbocation. Anytime you create a carbocation, look out for rearrangements and remember that it's flat. So when the nucleophile attacks, and in this case, I created my own nucleophile because Cl minus was the leaving group, it will come back in from the top or the bottom, and it will create this new molecule. That is the generic mechanism for an addition. Now, just some terms that I need to point out. So what does this syn addition and this anti-addition mean? Okay. Again, we are breaking a pi bond, and we're going to make two new sigma bonds. Syn addition means, let me see how to do this. Syn addition means that the two things that you create, and I'll just put X's. Okay, X does not mean halogen in this case. If they go on the same side, that's syn. Okay, syn means the same side. If they go on opposite sides, that's anti. And there are different mechanisms that will favor one over the other. So generically, you can have just addition. You can have syn addition, or you can have anti-addition. The one that I just did here is generic addition because it could be on the same side, it could be on opposite sides. Okay, these are stereospecific. All right, that is generic for addition. Now let me do one for an alkyne. All right, if you start with an alkyne, I'm going to switch colors again. And I'm going to do the same one, HCl. All right, again, I've got my pi bond. It is going to attack the hydrogen. It's going to kick out the chlorine. I'm going to make my carbocation. All right, and again, Markovnikov says this is the most stable carbocation. Once I have that carbocation, I'm going to attack. And so the first product I'm going to get is this. But I still have a nucleophile, okay? I still have a pi bond, and I still have HCl floating around. So we're going to do it again. Now again, where am I going to put that carbocation? I'm going to put that carbocation again in the Markovnikov location. And in this case, what is it going to do? This is still the most stable carbocation. And then again, from the top or the bottom, because it's a flat carbocation, and we are going to end up with notice they're on the same carbon, so this is called geminal. The key is that if you do addition for an alkyne, you will always do it twice. All right, go back to the top. So the generic mechanism, one of the generic mechanisms for alkenes and alkynes is addition. So you will break a pi bond, okay? You will form a carbocation. watch out. Every time you form a carbocation, you're going to look out for rearrangements. And then when you do attack, remember, you can attack from the top and the bottom. And then you're going to react with that carbocation and then watch out for stereochemistry. There's 3 generic types. I call it just generic addition, which is what this was. And then there's a specific syn addition and there's an anti-addition, and you will see examples of both of those. And then if you have an alkyne, remember to do that reaction twice. Unless, okay, this is a big unless you control it, okay? Only give it 1 mole, which is not very realistic. You can't just minimize and put 1 mole in there, okay? But unless you limit it somehow, it will, whoops, that's a T, limit it, it will go twice. Yeah, that's just the nature of the beast. All right, so that was your basic ideas behind alkenes and then the alkynes. All right, let's take a look at the first reaction. So I'm now looking at the reference sheets. And there we are. All right, so this is your reference sheet, and I'm looking at the very first one. Okay, so I've done a generic addition. So we are going to look at hydrogenation for both the alkenes and the alkynes. And go back to I should have realized I can just skip back and forth. All right, we're going to go all the way down to hydrogenation. All right, hydrogenation. Hydrogenation means you're going to put on hydrogens. We're going to do, again, alkenes, and we're going to do alkynes. Now, you are going to need some kind of a catalyst. So your catalyst is going to be platinum, palladium, or nickel. Okay, that's the generic ones. What we're going to do is we're going to form